thank you all for coming. I really appreciate you coming during the semester break, which is great. I know many of you are away, and hopefully you will see me in the video that's going to be put on the YouTube. So as you know, I'm going to talk about materials engineering and additive manufacturing. When I just thought about it, actually, I'm only talking about metals. So it should have been metallurgy in additive manufacturing, but I didn't have the heart to change that at the last moment when I sent it to you. So I left it there, but the next time when I talk about this, it will be mostly about metals. So it really needs to be metallurgy in additive manufacturing. There are, of course, processes that use other polymers and composites to deposit using additive manufacturing. I can talk about it if you just have an interest, but I can speak a little bit about that, not a lot. So I'm going to miss that a bit. The other thing I'll be talking about, this is even though I'm talking about metallurgy, I mean additive manufacturing, I'm not putting in any of the fun stuff like robots or how do you make the robots move or taking them on a rocket to somewhere, nothing of that sort. I'm going to talk to you about really mundane stuff that needs to be done in order to ensure that additive manufacturing is beneficial to the industry. And we can make parts using additive manufacturing that can be applied to industry. And that's the main crux of my talk today. So based on these caveats, I will talk a bit more. So first, we have to acknowledge the First Nations people across the lands on which we live and work, and we pay our respects to elders both past and present. And of course, I'm also mindful of the generosity of these First Nations people on which we live and work. So before I talk about additive manufacturing, so one of the things that I will talk about is conventional manufacturing. So even though the metallurgy of both these processes are really the same, but there are some peculiar things that happen in additive manufacturing. But first of all, we need to know what is this about additive manufacturing that is different from conventional manufacturing. So in general conventional manufacturing, you need to have a form. You know, many of the parts that you see have different shapes and sizes. So you should be able to manufacture them. So what are the different processes that are available to one to make these different parts? So I'm going to just touch upon some conventional manufacturing, which really are constrained to certain form using molds and dies, except in welding, of course, where you don't need to actually have any of those constraints. But even there, you know, it is constrained by the design, I think, anyway. I'm not fully formed my idea on that, but essentially additive manufacturing is free form, whereas the conventional manufacturing it's constrained within molds and dies, which you will see here. For example, I will talk about casting. I'm only touching on a few conventional manufacturing processes. So either this is essentially a transmission housing made of die casting. So you need a die to push the metal into a machine which has got the die, and then the molten metal solidifies on the die. And then here is another one, is a precision metal casting method. Then it also requires a mold, and then the rings are made using this. If you have any questions on that, let me ask me. So essentially, one more thing of this is the mold cavity, the one in the blue, and all the other bits, the mold, the molten metal is poured into this basin, and then it flows into the mold and runners and all that. So after the metal is solidified, you have to knock down this mold, and then also all the bits and pieces of that. So that's why it's kind of, you could call subtractive manufacturing. Okay. It's not very correct, but anyway, you have to remove some of them out. And then there is a little bit of finishing that is required. And even in additive manufacturing, you do need to do that. Then the other ones, you can see a number of rails, rods, channels. All these are made using another process, extrusion processes. This again are constrained in a die, and then they are made. So all these have a form which is quite different to other processes. And then there is also powder metallurgy process, which is very close to what we are going to talk today. You can see a gear wheel has been made, and then again it needs a die in which the powder is poured into, and then they are punched in, and then it has to be sintered and all that. So quickly, and then you have the welding. Again, you've seen big ships and bridges nowadays being done by welding. So these are all called conventional manufacturing methods, which require certain form, but welding alone doesn't require any of those forms. So we go to the next one, is the 3D printing. There are many processes that can be heat sources that can be applied to produce 3D printing. And here I'm not going to be talking about plastic ones, but I'll just touch upon some of these aspects here. You can also make different shapes and forms using molten or fused polymers that come through an extruded die you would have seen elsewhere. I think that's the one. You can see that that's a heating, and then there's a filament that flows through, and then the head moves as dictated by a computer. So for all this, we need the shape or the part to be put in a software, mostly a CAD. So Speed 3D people actually use Fusion 360. We use SolidWorks. So we work very closely with Speed 3D as well. So we hear whatever they say, because they are on top of their game. We ask them what is the latest one that they use. Then it needs to be put in a CAD file, and then this CAD file, one of the main things is, in the case of conventional manufacturing, the whole thing is done in one go, like you fill the mold cavity in one go, okay? Whereas in here, you have to build them layer by layer, which is what you would call digital manufacturing. So, and in all of this, again, you can see that something is moving, the heat source will keep moving as it is dictated by the shape of the product. And then there are, the layer size would be, again, dictated by how fine you want the form to be. And then how much processing that needs to be done at a later stage. And then, of course, the infill also is another matter, which will again dictate the strength of the part. So the one thing that I'm really keen to talk about in terms of the usage in the industry, I can't see. Can you see this carefully? Oh, that's a laser beam. Cool. So you have a laser beam on which powder is laid on a bed. And then the laser beam goes as per dictated by the shape in a CAD file. And then it takes, it melts the powder. And then when the powder is melted, the powders fuse together, and they all join together. So layer by layer, the depth of penetration would be only a few thousandth of a millimeter, you think? Yeah, that's all it'll be. So the powder themselves are only about 50 to about 50 micron in size. Of course, you can have larger sizes, but it may not fuse all the way through. So the laser beam is used quite extensively. It's called selected laser melting. You can also use an electron beam for that, but if you use an electron beam, then it needs to be in a vacuum, whereas with the laser, you don't really need to have that in a vacuum. Most of the prosthetics that are made are using selected laser melting. So they can be titanium, mostly titanium that is used, and sometimes magnesium and zinc are also used as metal powders to produce the form. For example, you can see here, one of this is again created by cold spray printing, and Matt has actually done that. I'll show you a video now in which Matt is actually displaying his capabilities as one who produces this part. So in general, if you wanted to produce a part, essentially the part in additive manufacturing is produced in layers. Okay, so it may be 1 millimeter, it could be, in the case of cold spray, it is about 1.6 millimeters is what they use. So that's how the layer gets built up. In electron beam, it's and laser beam, where the melting happens, that's even much smaller. And then you can think of the size of the beam being really, really small in terms of a few microns. So imagine that needing to go back and forth and cover the entire surface of the part. It's going to take forever. Okay, so the main thing that I'm saying is it requires melting. Okay, so if it does melt, especially if it is a highly reactive metal like titanium, then it requires an atmosphere that protects the metal from oxidation and from deterioration. Now, I don't know what the next slide is. I forgot what. What here? Oh, okay. Oh, okay. I'll come back to this one a bit later, but I want to show you there is another method of producing the same part. That is using solid state cold spray. So in this cold spray, I'll come back to this. So in here, you can see what is done is here.
You can hide that as well. Drag it out as a hide button. Just, yeah.
Oh yeah, let it stay there. Okay. You can see that it's got a pressurized gas that is heated in a gas heater, and at the same time, you also have powder that is transported through this pipe, and they all mixed in this mixing chamber, and it goes through this diverging converging nozzle, and at this point when it exits, it'll be the energy of the powder and the air is so large that it can be accelerated to nearly the twice or thrice the speed of sound. So now the particles, the heating is done at temperatures much below the temperature of melting of these powders. It can be an alloy, it can be a powder, simple elemental powder. So when they meet, when the powders hit against each other or against the substrate, they'll actually form bond in in solid state. Okay, so in order for this bonding to happen, what normally happens is, in general, metals, when left to themselves, they'll form an oxide layer on the top. Except for gold and platinum and palladium, all of the other metals will actually have, they'll not be found in the native state, they'll be found normally in a combined state. And same way, when the powder is hits against the substrate, it removes the oxide layer, and then two clean metals come into contact with each other and they form a bond. So thermodynamically, the two clean metals, when they're brought into very close contact, cannot stay that way. They'll form a bond, a metallurgical bond. I'm hoping this will work. So you can see that the deformation that happens actually removes the oxide layer, and then it forms a bond. So there are many other parallels to this idea. So if you have an explosive bonding, if you have one plate and have another plate on which an explosive material is put and then detonated. So this, if it is hit again, if it hit against the next plate at very high speeds, it will actually form a bond. And there are friction welding. And if you drive a car, the car wheels are made out of flash butt welding. Again, it's made in completely solid state in 20 seconds. It's all done, your car wheel. So all this is done completely in solid state. The whole idea is to removing this oxide layer and producing, I mean, when they should deform, and also the oxide layer should be removed. So that is the whole idea behind this cold spray. So the velocity at which the powder exits the nozzle will be about 3 times the speed of sound. And hopefully this works. Oh, yes, it works. So this is what is made. I'll tell you how this works. So this, we got a reactor here in amongst the audience. That's one. And this is the one that's made. Is this the one same thing? Or is this, that's a bigger one? Yeah.
That one might be slightly bigger.
Yeah.
So the one in the video is aluminium.
Yeah.
This one's stainless steel.
Yeah. Speed 3D, of course, is patented this process. So one thing that you would have noticed that the nozzle is stationary, and then the robot arm moves according to the CAD program or the slicing program. That is actually a proprietary software that's developed by Speed 3D to capture the particles and then make the robot arm move in a certain way as dictated by this proprietary software to take the shape of the part that you want. So one thing you would have noticed here is the shape is produced completely in free form. There is no constraint. Okay. So if you wanted to make any changes to the shape, you want to have another finger to this. For example, it can be done easily using a CAD. But at the same time, if you wanted to do the same in conventional manufacturing, it needs to be, you have to actually design a mold suitably or a die suitably so that can have the same in addition of another finger or whatever. So it takes a while for that to happen. Whereas with digital manufacturing, it is just a question of putting up, making changes to the CAD software. So that way, it's much easier to get parts to the market. So I'm going to talk a bit about a few other things. You would have seen, I talked about making bridges, big ships, large castings, and the like. At this moment, at least, there are no processes that make that kind of large-sized parts yet, but I think it will come, no doubt, in times. So you can see some of these sizes that are mentioned. So you can see that electron beam additive manufacturing seems to have a very large size part, nearly 6 meters and in height or width or whatever. Yeah, it's really large. And then there is also this company Titomic, which also uses cold spray method to produce additive manufactured parts. You can see it says it can go up to 9 meters, but that is done differently. That is, it's the entire system of delivering the powder is put on a gantry crane on large scale sized gantry crane, and then the powder is delivered at very using the same D-level nozzle, diverging, converging nozzle, and then the part is produced. So the delivery arm, it will be a lot more complicated than what we have in the case of Speed 3D's cold spray additive manufacturing. I think this is slightly old. With the recent ones, they can actually go even higher, right? With the light speed. It's an old one. It got 2021. It's not all that old, actually. So you can go higher, larger sizes. So one of the things that we are trying to do research is if you want something larger than what can be produced by cold spray, can we weld them together? Yeah. So that is a research that we are trying to do. What else have we got? Okay, that's fine. So I'll be talking a little bit about powders and some research that we are doing with Speed 3D and Swinburne. I will talk a little bit about it. So one of the main things, at least in additive manufacturing, is using powders. But there are processes that do not have to use powders. So you can actually have wires, weld arc wires, by welding. You can actually use a welding robot to do the same thing. And the deposition rate will also be much higher. But the finish will not be great. But there are some limitations as to what we can do with welding arc. If you involve melting, there are a lot of other issues that come into play. Certain metals will only dissolve in certain other metals in desired proportions. Whereas with cold spray, you can add as much as you want in there. And then if you have ceramic powders, they will most likely float out in a melted pool, whereas it's cold spray that can actually be included, and because it's completely in solid state, that can in fact be captured in the cold spray process. Okay, so having made the distinction between weld arc wires that can also be used for additive manufacturing, again built layer by layer, but most additive manufacturing processes would use a powder. So there are different ways the powders can be produced. And the shape of the powder also shape, size, and later we will see even the microstructure and hardness of the powder will dictate the quality of the parts that can be produced. So you can see some are really nice spherical ones, and they'll flow well in the delivery system. without getting clogged, I would think. Yes. You'll have views on that. And then you see this, then you can also have a powder that is produced by rotary atomization. So you melt the metal and then you rotate like a centrifuge, and that will produce powders of this nature. And then you can have gas to atomize the powder. So you have a molten metal, and then you have a gas go through it, and then it will disperse the molten metal into number of particles, and it will look something like that. But with one thing that you'll notice, it will also have some satellite spheres attached to these powders. I think this is again a gas atomized powder. What is it? D is, yes, gas atomized. And then you can see slightly irregular shaped powders are water atomized. So instead of gas, you use water to atomize the powder. So you can have different shaped powder. And apparently, I've been told from Speed 3D that water atomized powders behave better and get attached to the substrate in a much better fashion because of the irregular shape. That means the gas can hit the surface and produce greater force on the powder, so it can produce a bonding between the substrate and the powder. I think that's the theory, right? Yeah. Yeah. No. Yeah. So that also depends on the hardness of the powder and the microstructure in the powder. How are we going for time? Okay.
Yeah.
So this is the machine that we have here. We have taken this on lease. So we have CDU has got an alliance with Speed 3D, and we have this machine here. It's a small one, can produce up to 5 kilogram parts. Yeah. So some of the things that can be done, you can see here, most of the parts that can be done by cold spray. I'll talk a bit more about cold spray because I'm more familiar with it than other processes, is that it can replace most cast components. So if it can be done by casting, it can be done by cold spray, would be the way. So one more thing that in terms of properties of these materials, even though we say cast, there is a bit of an isotropy present in there, because if you put a mold and then you extract heat, the grains would grow in a certain direction. Whereas with cold spray, even though we're saying it's replacing cast component, the powder being really small and then it is well distributed, and even though it's in layers, and then after this additive manufactured part is put into heat treatment, it'll actually have a homogeneous structure. So that isotropy is actually lost in terms of the part being manufactured, which may be important for certain cases, but it's probably not possible for us to produce that kind of an isotropy. Otherwise, it needs to be designed into having materials with different properties. But directionality would be something that will be lost in this, whereas with casting, there is a certain amount of directionality if you don't do any heat treatment. And some of these parts that are produced using wires and the sheet metals cannot be made using the cold spray, but it can be done with laser and electron beam, but it's going to take forever to produce these. That's only. And very small parts, again, cannot be made using cold spray. but can be done using laser or electron beam methods. So, bit about why additive manufacturing. So one of the things that has been found is that many of the most of the manufacturing has moved to China. So I don't think there's much going on here, except for some welding companies. Most of the manufacturing, casting, or forging companies have moved. I hope they make the coins in Australia. But anyway, so that is one of the main reasons. So this is mainly because you have very high labor costs, and also because of the environmental concerns. Everything is sent away to China to be made into iron and steel and whatnot, and then brought back here. So because of this, now there is a great demand to reduce labor. So if you have digital manufacturing, you need only a very small shop. You must actually see Purple 13. It's really a small place. And Purple 7, again, there's a bigger machine there now. You can just send the CAD file over the internet, and then somebody sits at the machine, and then they have to press the send button and making sure that there is enough powder, and then the machine is heating the powder and the gases in the appropriate manner, and then we are done. I suppose, the file can be made in Japan or the US, can be just sent over the internet. So this type of distributed manufacturing is more suitable using digital manufacturing, and hopefully we don't need a large space. We don't need to deal with the number of people, and then the labor cost should also be less. And plus, we don't have to store things in a big warehouse. And of course, it also reduces and eliminates downtime. If your one is a farmer and the farmer needs a part to be done in real quick time before it stops raining or it rains, if you want the rain to come, then you want this part to be made real quick. So we will actually can make the part in really fast using this additive manufacturing, either cold spray, laser, or whatever be the means. So again, customization is one of the other things. As I said to you, you want to make a small change to it, easily done by changing the dimensions in the CAD file. So, and then if a part goes out of manufacture and it's no longer available, then you want to have the same part, and then you can easily make them, and that way you can eliminate any of the ongoing issues of maintenance and also obsolescence. I suppose, the parts engineered for 3D printing will probably never go out of production. So a few issues. Apparently, there are not many materials engineers in Australia or metallurgists in Australia. So all you people who are doing PhDs should seriously consider doing material science related work, because there is going to be jobs, I think, in the future, because they're talking about rocket launching facilities and whatnot. So this is an area that really begs more attention and sponsorship from people to take up materials engineering or metallurgy. Even in Australia, when I worked at Adelaide Uni, they were just closing down the materials engineering section. The other thing that we do is lack of application standards. So one of the main things that we are trying to work out is how do you specify parts that can be made using additive manufacturing. There are not many standards available, but they are coming, and that'll be a big area for industrial application of these parts. So that's no-brainer. In fact, you want to specify a part easily. You can say, I want a part to this Australian standard, and you can tell a supplier, I want this part to this standard, and you can get it, and this is what you're going to get. So whereas with additive manufacturing is still in nascent stage, and it'll take a while for this to happen. And again, I just mentioned to you about the size of the AM parts. You may probably have to join them together. There are other things such as heat treatment. You need to specify the right heat treatment to ensure that the parts have the right microstructure, the properties. So this is a big deal, and I will actually very quickly touch upon one of the things that we did with Speed 3D, especially with Tien, when she was the APR intern here, when she worked with Speed 3D. Now, of course, she's working for Speed 3D after that. Other thing is powder production. Most of the powders are now got from US and Germany. Yeah. So not many people who can produce powders, but there are some very specialty powders that we are trying to make here. Copper with alumina inside it, so it can have high temperature strength. There are very complicated procedures that are being done by people outside in the US and Germany to produce those powders. We're trying to do. I mean, of course, I mentioned about properties. You need to measure all these different properties for these ones and ensure that these can be applied in the industries. And lastly, the process speeds. So you can see that if you have a part and they have to be in layers, okay, this is how it deposits things in layers, yeah? And then each layer, you can see it goes, each one is a line, and then the beam, or in the case of electron beam or laser beam, you'll have to actually follow each of this line. Imagine how much it will take, how long it will take to do this. And the deposition rate is about 0.08 grams per minute. Yes, that's right, per minute. So it's really, really slow. Whereas cold spray would be at least 1,000 to 100 to 1,000 times faster. So these will take probably weeks or even months sometimes, if it's a large part. But it may not require any processing, but if it is a large part, then it might need a heat treatment to reduce the residual stresses. So one of the problems with this is time it takes to produce the parts. So now, anyway, most companies are now moving into a space where they can make 3D CAD models, so which can now be converted into slice, and this can be sliced using proprietary software that is used in 3D printers. Okay, so this is a work that was done by with Tien with Speed 3D. Of course, she had taken an APR internship, and we wanted to make copper nickel alloy. So this should have good antimicrobial properties, and also at the same time have enough tarnish resistance. So if you look at the handle outside, some of them are pretty bad. I think they're just brass with coating of nickel or stainless steel on the outside, or chromium probably, and they get tarnished. And sometimes if it is completely stainless steel, it doesn't get tarnished, but it doesn't have antimicrobial properties. So apparently it stays for few hours, few days. Yes, you know, during the pandemic, I mean, we are still in the pandemic. The problem was somebody touched with viral infection, and that virus is going to stay for a long time on the surface of the part. So one idea is to use copper. So copper is well known to kill the bacteria, but copper also gets tarnished very easily if you actually keep touching it. So the idea is now to look for a material that will have antimicrobial properties, but also it doesn't get tarnished very easily. So for that, adding nickel was one of the ideas. So you can have good lustrous surface, but also have enough copper to kill the bacteria that may be present on the surface. So this is 20% nickel, and then copper were mixed together, blended together, and then it was sprayed. Normal way of making these kind of part or coating is to have an alloy powder, a powder that has already got 20% nickel and 80% copper. But this is different. So we had separate powders of nickel and copper, and then they were blended and then sprayed. So when it was done, you can see nickel is there. It's just sitting there. Then it is just as sprayed condition, and it also has got a few voids. You can see because it has deformed. The powder is deformed, but it has got certain amount of voids. So the next step is to try different heat treatments. So these were heat treated for different times, and all of them were water quenched, and you can see it went all the way up to 1060 degrees Celsius for nearly 10 hours. And then there was also one that was heated for 1030 degrees Celsius, but air cooled. So you'll see what happened. So Tian is the one who should have done this, but anyway, quickly you can see that all of this have the water quenched ones all have voids in them. You can see these have large amounts of voids, and the one that was heated to 1060 degrees and water quenched, we believe that it's got large voids. We think that when we spray with so one of the other things I forgot to mention was with this cold spray method that is developed by P3D, is to use simply air, compressed air to propel the powder. Whereas all the others use either nitrogen or argon as the propellant. So we believe that because of that, the air trapped in between the powder is probably responsible for this flare up. That's what Tian says, and I believe that. Whereas the one that was made with heated to 1030 degrees Celsius and then air cooled produced the best part. And then when it was water quenched, we also think that it produced a large amount of porosity, which I think the dissociation of hydrogen and oxygen, we believe that hydrogen produced a huge amount of porosity on the surface. Whereas the air-cooled one, it had enough time for the air to come out, diffuse out of the surface of the metal, and it was mainly all right, I think. So what happened, I won't go into these ones. The hardness also is important for us to see that the ones at heated to 1030 degrees Celsius and air-cooled had the highest hardness as well. Interesting. And we also use stainless steel as a control medium to see as a negative control, in fact, see what happens to the bacteria. So you can see that after 30 minutes in copper, it's not there, whereas here, still there in stainless steel. So we think we probably developed a nice alloy, thanks to Tien. The material is also very lustrous. It is tarnish resistant.
So they'll be more expensive.
Which one?
They'll be more expensive, maybe.
It probably will be cheaper than. Oh yeah, it depends. Yeah, if it is the other thing, if you want to make it out of additive manufacturing, definitely it's going to be expensive, a bit more expensive.
But I think just a bit more, it's not more, a lot more.
No.
Because if you want to have a part that you design on specific part that you design, which is every point, but you get the part that you want to be in that shape and you want that probably it's very useful.
Yeah, it depends on what you want from this. Yep. So if you just want a coating, normally cold sprays methods are used for coating purposes. Yeah, maybe this is a way to go. And nickel is also nickel. I mean, in most stainless steels, if you add simply iron and chromium together, it'll form a stainless steel. But it will not have the bacterial resistance. So instead of making the whole handle out of copper, so have the coating of copper. Yeah, copper and nickel. That's one way of looking at it. So it may be cheaper actually. Okay, I'm just looking at the time. I got some more things, but I'm going to stop at this. I got the work of Swinburne as well, but I'll stop at this given the time. It's nearly. Any burning questions? Otherwise, I'll just stop at this. Any questions? Comments? Yes, please.
How do the properties of the manufactured items differ between additive manufactured and say cast? Things like strength and flexibility and those sorts of things.
It won't be very different. In fact, the additive manufactured part using cold spray would be better. Yeah. Because we can add anything that we want to this. There won't be any segregation that can be easily seen. Yeah, if you make a casting, you will have intermetallic segregation. Yeah, yeah.
And in an effort to be unbiased as well, SLM, the guys who use lasers to melt the material, you'll find that in some materials, particularly like titanium, they'll make it stronger than any other way you can make it. So whether it's raw, forged, or whatever, they blow it out of the water. So there's a bunch of parts, a bunch of characteristics to the process that mean that they're better than any other way you can make it. So yeah.
So one thing we are not sure about, even though I've not measured, I have not seen this anywhere else. Cast parts anyway will have very poor impact resistance. I would think the same thing would be with the cold spray. I would think. I'm not sure.
I don't know.
So it has not been measured yet. So that's a part. I'm not sure. In terms of other properties, we're fine. Yield strength and tensile strength, ductility, hardness will be all okay. Yes.
Do you use vacuum during cold spray?
What's this?
Show the device for the cold spray.
Yeah.
Is it vacuum inside or not?
No. I said they use air. So there's it's only for safety purposes. So you don't.
That can be impurities, right? When you manufacture, that can be if you're opening it and then closing it, if the room is not has impurities like dust or anything, it can go into the
We-
whatever you are fabricating.
If it is there in the powder, it will be, because if there is dust in the room, it will get blown by this high velocity airstream.
But still, it can also still settle on the.
Yeah, can. Yeah.
Because why I'm asking is, in case of my research field, you need highly pure things which are different from what you are doing, but.
No, if you want, it can be made. A clean room can be done.
Okay. So you can fabricate highly pure.
Yeah, you can have a filter the gas and if needed. Yeah, it's going to be expensive. That's all. Can make semiconductors also. They say with this type of method.
So what about one layer of one material and another layer of material?
Yep, can be done. That's the best part of this, right?
Oh.
So the character of each layer will not be changed dramatically. Whereas if you use laser, it will melt and it will alloy with each other.
What's the resolution on that? How thin can these different layers be?
It's at 1.6 millimeters. Was the thickness of each layer?
That's a surprise. I had the impression you had almost in microns.
That is that's only the laser ones. The laser or electron beam will be much smaller in terms of the layer height. Yeah.
So for fabricating semiconductor devices or something, you need the laser one and you can't use the pulse.
Can use cold spray is better actually.
But they are in the range of nanometers or micrometers.
Even with you need to find the powder of that size, right?
Which I think
No?
is easy.
I can answer questions if you like. I wasn't sure.
Yeah.
If you want to look at the video. So if they need to rethin it, you can just machine them, right? The way that we currently build materials with a 1.6 millimeter layer height, you can turn that down depending on whatever your application is. So that's just our standard build height. And that's mostly because it doesn't really matter for us. We're looking at building industrial sized 3D metal parts. So break it up into smaller pieces just makes it take longer, which in our case is a negative. So all about being able to make the part very quickly, hence we do larger layouts. We even go up to about 2.7 millimeters for some of our high deposition speeds, but it can be turned down just in our applications, there's no point. So CSIRO, for example, do lots of very, very fine detail cold spray, and they'll do it on the micron level. So you typically look at like 30 to 50 microns, depending on the powder feedstock that we're using. But yeah, very different application from what we do. Same process, but it's like saying, there's lots of different types of welding, for example. So all of them are good at different things, or all of them can be made to do different things. But the base technology is effectively the same. Yeah.
Yeah. You can, if you had nano powders, then you can run laser or electron beam.
Yeah.
For the polymer solar cells, I'm not sure about this, but for polymer solar cells, we have a last layer which we deposit, which is aluminium, and then for that we use thermal vapor deposition. So, do you think we can replace this thermal vapor deposition with hot spray method? Because whatever is underneath is polymer material, so I don't know if those particles will go inside.
Yeah, they might probably destroy that layer.
Just like
So you would need to make your layer a different way, or at least there'll be different preparation techniques beforehand. So yeah, so it's like photo etching and things like that, fairly common methods for lots of this stuff already, and you can use them in cold spray, which is part of that process. Yeah, you can use photopolymer plastic printers as well to do similar stuff what you're talking about, which is very cool.
So you can buy a aluminum film and put it on top of that too. You don't have to use cold spray. Yeah.
No, because that will create impurities in between. the film will create impurities in between the polymer material and the aluminum layer. There should not be any impurities in between.
Yeah, put it in a clean room and do it.
And all the gas in our process is filtered too, so there aren't any impurities. But it is air. It's filtered compressed air.
I don't know. Anyway, I've just only touched upon some of the things, and I try to keep it at a level that is conducive for all the different audiences. So, thank you. If you don't have any other questions.